the audience background is going to be fairly broad, so I'm going to try to keep the lecture also somewhat broad, but feel free to jump in and ask questions whenever you feel like it. So you're not going to see a lot of equations or anything of this in this presentation. Okay. Okay, so the topic of my talk today is the evolution of data center network architectures. And first of all, I wish to thank IEEE for sponsoring this tour, and to Sasha and the New South Wales chapter for inviting me here to Wollongong. Okay, so let me start by saying, how many of you are familiar with data center networks? No, so this is going to be fairly new to most of you, I suppose, if not all. Okay, so first let me give you an overview of what data centers are. And they enable cloud computing, which I'm sure everybody is aware of. So what is cloud computing? It's basically large-scale computing that offer what are called as XaaS, where X is either infrastructure or software or platform. So examples of these things abound, and all of us use these things in one way or another. For example, infrastructure as a service. And this is offered by Amazon, Amazon EC2, or Elastic Compute Cloud, where anybody can lease virtual machines off of the Amazon cloud and run whatever compute jobs they have. And this makes it a lot easier for not just individuals, but for even companies to run their operations. For example, Netflix. All of the movies of Netflix are hosted on Amazon. And you don't realize that this is done, but even a company as big as Netflix actually uses Amazon EC2. In fact, the Amazon EC2 has a larger retail operation, or I should say larger revenue than the retail part of Amazon, which is not very widely known. So what are data centers? The data centers are basically the infrastructure that do all of the number crunching, that enable cloud computing. Right? So it basically consists of a lot of machines, a lot of commodity servers that are connected together and that collectively and distributively process large data jobs, large big data jobs. Okay? So that's what data centers are. And data center network is, of course, the network that interconnects all of these servers in a data center. Right? So this is just one aisle of a Google data center. So all of these things that you see here, these are the servers. So each one is one computer. And you typically have a rack with a few tens of servers that are connected by a switch that sits on top of the rack. That's actually called the top of the rack switch, or a TOR switch. And then these racks are interconnected through another network. So my talk today is going to be focused on that particular aspect. Well, why is this important? This is actually just one aisle, or one row of this data center network. There could be hundreds of such aisles in one data center site. So it's really big, and the network is really complex, and it consumes a lot of energy. Okay, so these are very important things. Right? So that's a, this is a little bit dated. This shows from 2012 to 2017, the growth of data center traffic. So the growth is kind of, you can see that it's growing pretty quickly there. And well, Intel estimates that connectivity of these data centers is estimated to be an $11 billion industry. So there's a lot of money riding on this. So my talk today is going to be focused on how to construct, how to design, or to architect a network for so-called hyperscale data centers. These are the really large data centers, Amazon being one of them, right? So there's a lot of these data centers, about 500 of them globally. And this is kind of how they're distributed. About half of them are in the US, and the big ones are known to everybody. These are the Amazon, Facebook, Google, and Microsoft. They are considered the 4 largest data centers. There's some big ones in China. The 3 biggest ones there are Alibaba, Tencent, and Baidu. But they're everywhere. In fact, there's a lot of data centers. Amazon by itself runs about 100 data center sites, and there are about 38 of them in Northern Virginia, and I put it there because that's in my neck of the woods. And there's 8 of them in Sydney, which is your neck of the woods, right? So the typical data center consumes about 15 megawatts of power, and that's a huge amount of power, right? So it's very important that we bring down this power consumption because it has a lot of impact. Okay. So that's what this talk is going to be about. So any questions before I move on further? Okay. So I don't know how many of you have a background in networking as opposed to just data center networking, but I'm going to contrast what is special about data center networks as opposed to any network like the internet. Okay. So data center networks versus wide area networks, what's the difference? Well, it turns out that the characteristics of the applications that you run on a data center are somewhat different than what you may run on the internet. Okay. So the data center network applications typically require both high throughput, that means you need a lot of bandwidth, okay, as well as low latencies. Okay, low latencies is very short response times, right? So you need both of them. And there are some things that are used in the internet that do not happen in a data center network. For example, there's something called statistical multiplexing, which can be taken advantage of in a wide area network, and that is not seen much in a data center network. On the other hand, on the positive side, data center networks are largely homogeneous. That means they are pretty similar looking. All of the servers are usually from the same vendor, and the networking equipment is also usually from the same vendor. So there's a lot of homogeneity in data center networks. Okay. So another characteristic is that there are a few what are called as elephant flows and a lot of mice flows. So elephant flows are traffic flows that generate a lot of data, okay? Megabytes, gigabytes of data. So there are just a few of them, whereas most of the flows, most of the traffic flows in a data center are actually very small, a few kilobytes, a few bytes even. And that's the vast majority, more than 90% of the traffic. So you have these very small flows competing with very large flows, and you have to design the network so that the large flows don't swamp up the small flows. Okay, so finally, most of the traffic that arises in the data center actually lies within the data center. In other words, the data center is connected to the internet, of course, because the internet is where the queries occur. If you have a Google search, that comes from the internet to the data center. The data center is where all of the processing is done. But most of the traffic that comes out in this process actually stays within the data center. It's just the results that are returned to the user, which is a very small part of the actual traffic that goes on. Okay, a single Google search sometimes, I heard somebody from Google say this, a single Google search can generate terabytes of data to be transferred from one machine to another machine within a data center. So you need very large amounts of bandwidth, and the latencies have to be very short. So here is some of the requirements of a data center network. First is it needs to scale modularly. These are very expensive, as I will show some numbers later on. Okay? So the data center needs to scale modularly. That is, you don't want to build a huge data center when you don't have enough traffic, but you should be able to grow to a large one in a fairly easy way. Right? As I mentioned earlier, there's a need for both high throughput, which means high bandwidth, and low latency. Okay, both are needed. Now, low latency is very important. For example, OLDI stands for online data intensive applications. So web search is an example of an OLDI application. So these require very low latencies. Okay, what do I mean by very low latencies? In the order of milliseconds. Okay, 100 to 200 milliseconds. Now Google did a study actually and found that if the results for a web search, if it's delayed by half a second, then they lose 20% of revenue. So this has tremendous impact for these kinds of companies, right? So that's half a second for the entire web search results to be displayed to the user. Okay. Now internally, they set much stricter deadlines on various jobs that are needed to be run to generate those search results. Okay. Typical examples are 100 to 200 milliseconds. Okay. Now the data center is contained in a single large warehouse-sized building, okay, where the propagation delay, the time it takes for a bit to flow from one computer to another computer, is in the order of microseconds because the distances are very short compared to the internet where you have bits flowing from one continent to another continent, right? So the propagation delay is very small, but still there are other overhead delays that need to be kept down in order to achieve these latencies, right? Okay, So they must be agile, which means the network must be configured based on where the traffic is. It's impossible to hook up every pair of machines at the full speed that they are going to generate, right? That's impossible because there are going to be thousands of machines in a data center, right? So you have to have a network that can be configured quickly when the traffic changes, and the traffic does change very often in a data center, right? Fault tolerance. So faults are actually the norm rather than the exception in a data center because these contain hundreds of thousands of commodity machines. So any one of them can fail at any time, at any given time. Okay, obviously we need low power consumption, I already mentioned that, low complexity, and low cost. I mean, these are pretty much given for any system. So here is kind of how the cost is distributed among the various components. The servers themselves, the machines themselves cost about half of the entire data center. And then there's the infrastructure, the building, cables, and so on. That's at water. And electricity is 15%, and the network is 15%. Okay. So this talk is going to be focused on the network side. Okay, so I'm going to look at the various ways in which these computers in a data center can be connected together. Okay, so I'm going to talk about how this network has evolved over a period of time and what the problem with the original network architecture was and why these new solutions are needed. Right. So this is the conventional data center network architecture. Okay, so what you have at the bottom are the servers. These are the machines. And here is the switch at the top of the rack. As I mentioned, this is called the TAR switch, or the top of the rack switch. So this is one big unit, about as big as this, right? Contains a few tens of machines, right? So these have to be connected together in some way. And this is how traditionally they were connected. You had a bunch of switches. These are Ethernet switches that connect, each of these racks connect to multiple switches for fault tolerance purposes, and these switches are in turn connected by other switches, and it's a hierarchical, tree-like structure, right? So this is how it's traditionally done. So this is what we call as layer 2 because this is mostly Ethernet, and when we go here, this is doing IP routing here. So those are AR aggregate routers, and then you have core routers which are connected to the Ethernet. So this is the traditional way data centers have been built, right? Now, what's the problem with this? The problem with this is that the links at the top require very expensive non-commodity switches. Oops, sorry. Right there. These things. These require non-commodity switches. They're very expensive. They have to be custom made. Okay. There are also a number of problems. You couldn't balance the traffic. You couldn't make sure that all of the bandwidth that's available in the network could be effectively utilized. Okay. So there may be a lot of traffic in one portion of the network, but the bandwidth may be available in this portion of the network. So it couldn't match the network and the traffic. Okay, so there were those kinds of problems. Okay, so a number of alternative architectures have been proposed, and I'm going to show you one such architecture, one standard electronic architecture, and then talk about optical architectures which work in a completely different manner. Okay. So here is, before I get to that, I just want to talk a little bit about what is called as a class network. Okay, this is about as technical as it's going to get in this talk. Okay, so a class network works as follows. Okay, so these are switches here, and these are n by m switches. So n inputs, and you have m outputs. So m being larger than n. Okay, and you have r of these switches. So there are n times r inputs right here, and you have to connect these n times r inputs to these n times r outputs. Okay. Now, the complexity of the switch is a very important one. You could build a single big switch with NR inputs and NR outputs, but if you want the switch to be non-blocking, which means if you want to be able to connect any input to any output, the complexity of the switch is too large. It's too prohibitively expensive. So you just cannot do that. Okay. So finding less complex ways of achieving this switching has been a topic of research for a long, long time. So class, this is in the 50s or 60s, it's been around for a few decades, came up with this kind of a structure for the switching network where you have much smaller switches like here, and you have a larger number of intermediate layer switches, and then you have the same number of switches on the egress side as in the ingress side. Okay, and he showed that if you have a sufficient number of switches here in the middle layer, then you can achieve this non-blocking property at a much smaller complexity than your single big switch. Okay, So this is what Klaus showed. Now, if you take this switch architecture, this is like a book that is open. So this is the spine of the book, and this is the left edge and the right edge. So if you close the book, this is what you get. This is called as a folded glass architecture. Okay? This is the spine, and this is the leaf. Right? So this leaf spine architecture has been used for some time in data center networks, and that's what this figure shows here. This is from this is a figure from Intel. So here are the racks at the bottom, and this is the leaf switches, and these are the spine switches. And then you can have additional layers if you need to, called super spine core switches. So these are the interconnecting cables, and these are typically optical fiber optic cables here. Okay. Okay. So the alternative to the traditional switch architecture, which required all these expensive switches at the top, was the so-called factory architecture. Okay, it was developed by these folks and was presented about 10 years ago in this conference, SIGCOM. Okay, is this so-called factory? It's called factory because the links towards the top have higher bandwidth than the links towards the bottom. Okay, and it works as follows. And the cool thing about this is that all of these switches, these are the switches here. These are servers at the bottom here, and they show us this computer here with a keyboard. Okay, these are switches here. All these switches are identical switches. Okay, they are the same. In this case, 48 port gigabit Ethernet switches, and the top one actually 10 gigabit Ethernet switches. But these are commodity switches. There's no need for any expensive switches. That's what this factory architecture authors showed. Okay, and the architecture is as follows. So there are K pods. K is 4 in this example right here, and each pod has 2 layers of K/2 switches. Okay, so these are the edge switches, and these are the aggregation switches. So K/2 is 2 in this case. So 2 switches here, 2 switches here, and there are K/2. Where's the code? K/2 squared core switches. So each of them connects to K pods. So these are the core switches. Okay, and ignore these numbers here. That's for the addresses that they allocate for doing routing and so on. Okay, so the way it works is that with a K factory switch, you can support K cubed over 4 servers. So in K is 48, which is a standard size for an Ethernet switch, you can support 27,648 servers. So which was a fairly large size, and they showed, using a number of studies, that the power consumption and the complexity of this network was much lower than previous designs. Okay? It also provides a lot of paths because, as you notice here, if you want to go from one machine to another machine, one server to another server, you could go to these K/2, any one of these K/2 other switches, and from here you can go to any one of these K/2 core switches from each of these switches. Okay, so there are actually K/2 squared paths. So when K is 48 for this size network, 48/2 is 24. 24 squared is 576. So there are 576 paths between any 2 machines. So very rich connectivity. Provides a lot of bandwidth, right? However, this is a static network. It's not configurable. The network is this. You cannot change it. Okay. So now this is an electronic architecture. This is the state of the architecture on the electronics side. Okay. So now recently there's been a lot of work on incorporating optics in this data center network. Okay. Now to be sure, all of the processing is still done electronically, right? All of the number crunching. So everything, the signals have to be electrical signals. Okay. But the transmission today is done optically. But now, what are these optical architectures? They actually introduce a little bit of optical switching into the network. And why is that important? Well, I'll show you something which will convince you, hopefully, that it's needed. It's mainly because it's got very large bandwidth and very low power consumption. Okay, so those are 2 very important things that are needed in data center networks. So I'm going to go through a few of the architectures here. First of all, let me point out some of the one big distinction between electrical switching and optical switching. Okay, so the way electrical switching works is that if you want to transmit something, you put it in something called as a packet, right, which is a few bits, and the packets are transmitted from one node or one machine to an intermediate switch. The switch is going to actually receive all the bits of the packet, store the packet, and then it's going to retransmit the packet to another switch, and so on. Okay? So this is called a store and forward switching. Right? Okay. On the other hand, the optical side, it's completely different because the technology is completely different. Okay? It's not possible to store light. Okay? Such technology does not exist. It's possible to slow down light a bit, but it's not possible to store light. So there is no such thing as an optical memory. Right? So memory is basically storing things. Right? So if you cannot slow down light, then you cannot store it anywhere. So there's no optical memory. So once you transmit something, you cannot slow it down in the middle. It has to just go until it's received, until it's converted back to an electrical signal. Right? So because of that, when you do optical switching, what you do is basically you transmit a signal using light. This is actually infrared light, not visible light usually. Okay? You transmit the data in the form of light, and the switches are set so that your signal is going to be switched to the intended receiver. Okay? This is just like how your phone call switch works. Right? When you transmit something, the signal is not stored anywhere in between, but it's just directly switched all the way to the receiver. Okay? So it's a fundamental difference between how packets are switched using electrical switches and signals are switched in optical switches. So the switching technology is different. Here it's store and forward, and then it's circuit switching. Okay, so this kind of shows how a optical switch works. It uses MEMS, micro electromechanical systems, MEMS mirrors, and here's input light, and there's a bit of an animation, which is sometimes hard to see because it's white in color for some reason. But you see that arrow that went through there. So basically, it goes to a mirror array, and the mirror array can be, each of the mirror contains a lot of mirrors. Each of the mirrors can be tilted to whatever angle you want. And based on how you tilt the mirrors, and this is another mirror array, so how these mirrors are tilted, how these mirrors are tilted, basically determine where the light is going to be collected, which output the light is going to be collected at. Right? So that achieves your switching. So by changing the mirrors, you can send light to a different output than the previous one. Okay? So this is how the optical switch works. Now in terms of the switch capacity, the optical switches have a much higher capacity than electronic switches. So here is a state-of-the-art Cisco switch, 16 by 40 gigabits per second. Okay? That's 640 gigabits per second. Whereas here is an optical switch, 320 by 100 gigabit per second from this Cadmium fiber connect switch. Okay? So it's orders of magnitude larger than the capacity of an electronic switch. The problem here is the switching time. Okay? The electronic switches are very fast. They can switch at packet granularity, which is microseconds or nanoseconds. Whereas optical switches are rather slow. It takes about 10 milliseconds because it's mechanical. You need to change the mirrors to change the switch, right? So it's much slower than electronic switches. The problem with optical technology is that the switches are slow and there's no memory, okay? But the advantages are high bandwidth, low power. So how do we incorporate optics at the best and overcome the problems of optical switching, right? So there's been a lot of designs that have done this. So here are the advantages and drawbacks of optical switching. Very high capacity. Okay. So fiber optic transmission uses something called as dense wavelength division multiplexing. Okay. Basically, the bandwidth is partitioned into disjoint frequency bands, and each of these frequency bands can be used to send a distinct signal, distinct data stream. Okay. At very high rates, each of these streams can be up to 40 or 100 gigs each. In fact, just last week at a conference, a company demonstrated 800 gigabits per second on one wavelength channel. Okay, so this is tremendous. 100 wavelengths of the order of 160 wavelengths times 800 gigabits per second. So we're talking about 80 terabits per second, 100 terabits per second and more in a simple fiber, right? Okay, so there's a lot of low power consuming components, and I'll talk briefly about some of these things that can be advantageously used in this architecture. So a very important thing for optical switching is that it's agnostic to data rate and format. What I mean by that is when you set up an optical circuit, okay, it doesn't matter what kind of data you're sending through it. It doesn't matter what protocols you're using to send the data on. Okay? The electronic switches, they are very aware of the protocol because they have to process the data. They look at the header of a packet and so on. Nothing like that happens in optical switching. Okay? It only looks at the frequency of light and does its switching function. It doesn't look at what's the content of the data, what format, what kind of signals are being used, nothing of that sort. Okay? So it's a very big advantage because you can change your protocols, your protocols for transmission and so on, and not change any of the hardware because the switches don't look at this information. Okay? The problems or the drawbacks, as I mentioned, are the slow switching speeds related to electronic switches, relatively expensive, okay? But prices are continuing to drop, and it's relatively immature technology compared to electronics. For example, there's no memory, right? So you've got to overcome these problems. So I'm going to talk about a few architectures that have used various types of optical components in this. And then finally, I'll show some results on how much power can be saved and so on. Okay? So the first one is something called a see-through. Okay? So here's what they did. So these are the racks here, right? Racks of servers, as you see here. And this is your conventional tree architecture, the electrical network, right? So I said, okay, we're going to have that thing because you can't do everything with optical switching, but I'm going to augment this traditional network with an optical network. And they did that by just using a single optical switch. So this is an optical switch. Okay? It can't connect every pair of these racks, okay? Because this is a large, you have hundreds of thousands of these racks, right? Or at least thousands of these racks. You cannot connect every pair of these racks with a single switch. But you can selectively connect a few of the racks where there's a lot of traffic. Okay? So that's the idea. So, but since we cannot connect everyone, we do need an electrical network on top there. So if you cannot use this optical switch, then use that. But try to use the optical switch if you can. So that's the idea here, right? Okay, so this is an electrical packet switch network for low latency delivery and an optical circuit switch network for high capacity transfer. Okay, so for those flows that are large flows, those gigabits per second and terabits per second flows, you can use the high capacity optical switch. Okay, for the other small flows, use the electrical network. So this was their idea, and you can reconfigure the switch, but at very large time scales, very slowly. Okay. So they showed that it's possible to estimate the traffic demand and then configure the switches and let the sources or the racks know which pairs of racks are connected by the optical switch. Not every one of them is going to be connected, but it's going to let them know which ones are connected. And if there is a connection that exists, then try to use that optical circuit. Okay? So traffic demands come in, you reconfigure the switch according to where the most traffic is, and then let them know. Okay, so those are the pairs of racks that are connected. Okay, so traffic is then split between the top network and the bottom network, and for this they use basically two what are called as virtual LANs. So every packet is going to be tagged with either virtual LAN 1 or virtual LAN 2. Virtual LAN 1 is the top one, and virtual LAN 2 is the bottom one. Basically, they showed that you can do this without changing any of the servers. Okay, you don't need to change the hardware or the software on any of the servers in this, or the switches. Okay. All right. So this is a very initial, somewhat rudimentary design, or rudimentary now, okay, of incorporating optics into a data center network architecture. So a much more advanced one is called this Proteus, or OSA optical switching architecture, which was presented in 2013, about 5 years ago. Okay, so this is what we need, right? So we have a bunch of racks here with a TOR switch on top, and any kind of traffic between these servers is handled by this TOR switch. So that traffic never appears outside of the rack. Okay, so we're only interested in looking at how do we connect these TORs together, okay? These racks together. Okay, So their goal was this. So what do I need to put in here to achieve these goals? Okay, so here it is. So each TAR looks like this. Okay, so it's got a bunch of optical transceivers, one at each wavelength. Okay, and this one shows 32 wavelengths right here. Okay. So any traffic within the rack is never going to appear to the optical side. Okay, it's going to be switched internally within the rack. Okay, they're not changing any of that stuff. But if there's traffic that is coming from outside the rack to this rack, then that's going to come in through the optical port, right? Like that. And this could also be used to switch some transit traffic. So this is hop by hop traffic. So transit traffic, that is, the traffic is not really destined to this rack, but this rack is being used as an intermediate switching point for some other traffic. Okay? So traffic comes in optical form here, the signals come in as optical form. They need to be converted to electrical form here and then transmitted on another transceiver back out to another interface to wherever it's going. Okay? Like that. Okay. So we still haven't decided what kind of optical components go there. Suppose there is one TAR here, TAR 1, and I have a bunch of other racks, right? Or TARs. Suppose I want to connect to these TARs, to these 4 TARs, right? Because I cannot connect to every TAR. At this point of time, this is where I have most of the traffic too. So I'm going to choose to connect to these 4 TARs, right? How do I do that? Further, the traffic to these TARs may be not uniform. What I mean by that is, so you have all these wavelengths that are going to these optical components here, and maybe this is what I need. So I need 2 wavelengths to this TAR, 1 wavelength to here, 4 to this one, and 1 to here. In other words, the traffic is not uniform. Okay, so there's much more traffic between TAR 1 and TAR 45 than between TAR 1 and TAR 21 and 73. And obviously, to the other TARs, we don't have a connection. Okay, so you have to go through one of these TARs and then switch to the other TAR if you want to send something to the other TARs, right? Okay. So, and the traffic may not also be symmetric. So here you have 2 wavelengths, you have 3 wavelengths worth of traffic. So each wavelength is, at that point of time, it was 10 gigabits per second. So if I have 2 wavelengths, that means that's a 20 gig connection, right? So how do I get this kind of connectivity, right? So I want a high capacity link to some TARs, a low capacity link to some TARs, okay? And I want to be able to change the capacity dynamically, right? For example, later on, I want to change the topology. So I want to change the topology so that I don't connect to those 4 TARs that just dropped off, but to these 4 TARs, because now the traffic has changed, and I don't want to connect to the same 4 TARs. I want to connect to a different set of 4 TARs, right? How do I achieve all of this stuff? So I want to be able to reconfigure reconfigure my topology to achieve this. Okay. Okay. So to do that, I want to talk a little bit about some of the basic optical components that are used. Okay. There's a lot of physics behind this. I'm not a physicist myself, so I don't know how they operate, but I'll tell you from a conceptual point of view how they operate. They're very simple devices. Okay. So one of them is called as a coupler. What a coupler does is you have 2 signals on 2 different fibers, and it's a 2-port device. Okay. And the power from these 2 signals are combined and distributed to these 2 outputs. So you could have a signal on one wavelength here and a signal on another wavelength here, and they can be combined, they are added, and then they are distributed across these 2 outputs. So if you have a signal on lambda 1, wavelength 1, and a signal on lambda 2, they're combined, and each of the outputs you get a signal on both lambda 1 and lambda 2. So it's an easy way to combine multiple signals onto a single fiber. Okay? So that's one. Then there's a device called as the circulator, which is a directional device. It has the following property. So if you send a signal here, and that signal appears here, but it doesn't appear here. So when you send a signal on a port, it appears on the next clockwise port, but not on the 3rd port. So this is called as a circulator. So if you send it here, it appears here. If you send it here, it appears here. If you send it here, it appears here. but not the other port. So this is a pretty cool device. Turns out you can use this to achieve bidirectionality in many of these designs. Okay. So here's one of the most important components called as the wavelength selective switch. Okay. So this is the technology is very complex in this one. So it's got one input port, and let's say there are n output ports here, and this is a fiber with a certain number of wavelengths on it. And what the switch is able to do is it can be programmed to send each of these wavelengths independently to any one of the output ports. So I can say, you know, I want to take this red wavelength and send it there, and the green wavelength and the blue wavelength. And then the orange and the light green go here, and these lime green, yellow, etc. to those ports. So I can do this. So I can send any wavelength to any of the output ports, and I can change this. I can change this. Okay, so at a different time, again, the change is done in millisecond time scales. Okay, so at a different time, if you want to have the red wavelength go here, I can do that. Okay, so this is the kind of switch that's available now. But the problem is the number of outputs is right now is restricted to very small numbers. You can have 4 outputs, or 9 outputs, or 20 outputs. These are typical sizes for what's commercially available now. Okay, it's a pretty expensive device, but it provides a lot of flexibility. Okay, so here is their design. Okay, the Proteus or OSA design. So I mentioned there's a layer of optical components here. Well, what are the optical components? Well, these are the optical components that they came up with, right? So this is a TOR, and this is a TOR. They have 32 wavelengths. So you have 32 optical transceivers here, and these wavelengths are first multiplexed by using a coupler into a single fiber, and then you have a wavelength selective switch that can split these 32 wavelengths on demand to whatever number you want. So it splits it 4 ways. So I could have 8, 8, 8, 8, or 10, 15, 5, 2. Right? So I can split this 4 ways, any number of wavelengths on any of the ports. Right? So that allows me to change the bandwidth to each of the other TORs, each of the 4 other TORs that this TOR is going to be connected to. Okay. On top of this, there's a MEMS switch, and I showed you how a MEMS works by tilting mirrors, right? So that's a switch which allows me to reconfigure the other TORs to which I can connect. Okay. So this WSS allows you to change the bandwidth of the links on the connections to the other 4 other TORs, whereas this one determines which TORs you connect to. So you can change both the topology and the bandwidth of the links in that topology. Okay, so this is using existing optical components. Okay, and that's on the receiver side. Okay, so you get bidirectionality with circulators, and the capacity is changeable with the WSS and wavelength selective switch, and the topology is changeable with the MEMS switch. Okay, so there's some animation here that shows you how this is split. Right? The wavelengths are. Okay, so they prototyped this design with a 2,516 rack design. 2,560 servers, 80 racks, and 32 servers per rack. And they used a 4-port WSS, where the capacity of each of those links can be changed in number of wavelengths. Each wavelength is 10 gigabits per second, so you have 32 wavelengths. So the bandwidth of the link can be changed from 10 to 320 gigabits per second in multiples of 10 gigabits per second. Right? So if you don't have direct connection to a given TOR to which you're sending traffic, then you have to use hub-by-hub connections to the other TORs. Now you keep in mind that this incurs latency, because the low latency is to a TOR to which you're directly connected. Now if you're going to use the other TOR as an intermediate hop to get to another TOR, that incurs a lot of latency, not to mention extra power, because converting from an optical signal to an electrical signal takes a lot of power. Not to mention latency, because you have to store the signal and then send it back as an optical signal back out. Okay, so using another TOR as an intermediate node is not desirable. It does take a lot of time. Okay. So the final design that I'm going to show you is a design that we have come up with. Actually, it's hot off the press. It's not being presented in public yet. So it's going to be presented in a conference in Shanghai next in May. Okay. It's called RODA, Reconfigurable Hierarchical Optical VCA Architecture. Okay, so before I get to that, I want to introduce one final optical component called as the Arrayed Waveguide Grading Router, AWGR. Okay. This has the following property. So this is the router. It's got 4 inputs and 4 outputs. In practice, it's got a lot more inputs and outputs. This is just a simple example here. And let's say there are 8 wavelengths here. Okay, so I've got 8 wavelengths on each of the inputs, right? Each of the fibers. Now, what this device does is it switches these wavelengths to these 4 outputs depending on what wavelength they are. For example, lambda 1 is switched to this output from here. Lambda 2 is switched here, lambda 3 here, lambda 4 here. Then it goes back, lambda 5, 6, 7, 8. So it's got this cyclic routing property. Okay. It routes the wavelengths to successive outputs, and if there's more wavelengths, starts over at the beginning and then routes at the outputs. Right? So this is fixed. You cannot change this routing pattern. Okay, this is fixed. It's a passive device. Okay, it's built that way. Okay, and because it's fixed, the device consumes no power, 0 power. Okay, it can be built for fairly large port counts, so you can have hundreds of inputs, hundreds of input fibers, hundreds of output fibers. Okay, this here shows the switching matrix for this particular grading. So you cannot change the switching pattern, but it does provide some switching, some wavelength-based switching. Okay. Turns out that this is actually a pretty nifty device. Okay, it can be used in a design. Okay, so here's how we use it. Okay, now this looks pretty messy, but I'm going to break it down and go over what each one of them does. So the basic idea is this. So you have a large data center, let's say, you have hundreds of thousands of racks. Okay, now you don't need, at any given time, the traffic is really restricted from a given rack to only a few other racks, not to all of them. Okay? Obviously, to which racks, that changes from time to time. Okay? So that's why we want the network to be configurable. But we don't need full bandwidth from one rack to every other rack at any given time. You only need it for a small subset of the racks. Right? So that idea, okay, I mean, that observation basically leads us to the idea, why don't we combine these racks that have a lot of mutual traffic between them into a single cluster and somehow provide high bandwidth to those racks within that cluster. Now obviously I need to be able to reconfigure this cluster because this traffic is not going to stay static, right? So at one point of time, as I said, rack 1 may be having a lot of traffic to racks 5, 6, 7, and 8. At another point of time, it may be 9, 10, 11, 12. Right? So I should be able to change the definition of this cluster. Okay? So the idea is, if I can group these racks with high mutual traffic together as clusters, okay, then I provide a high bandwidth network within each of those clusters, and yet provide some kind of connectivity between those clusters. Right? A lower amount of connectivity. Then this is desirable, right? Because now I'm allowing for the reconfiguration of clusters and also the reconfiguration of the topology that connects these clusters. So this architecture has all of these elements. Okay. So let's see how this works. So I'm going to, it's got 5 different parts actually. So it starts with this. That's the cluster membership network. So what this does is it basically allows each rack to be grouped with a subset of the other racks into a cluster. Okay? Now it turns out if you want to do full flexibility in this, that is, if you want to take any set of racks, the cluster size is going to be fixed. For example, 16 or 32 or something like that. So let's say it's 16 racks in a cluster. So if you want the full flexibility of taking any 16 racks and putting them in a cluster, then it turns out that that configuration part is going to be very complex. So what we've done here is we've tried to provide a trade-off between the complexity and the flexibility. So by trading off this, instead of saying that I don't want the full flexibility of having any 16 racks in a cluster, But most of the racks, maybe I should be able to pick from most of the other racks, if not all of the racks, okay, to form a cluster. And that reduces the complexity of switching quite a bit. Okay? So that's what this alpha parameter here is designed to achieve. Okay? So you can trade off complexity with flexibility. So basically this part allows groups of racks to be configured together as a cluster. Right? Then there are two kinds of communication now. Once you form clusters, there's intra-cluster communication and inter-cluster communication. Right? So basically you partition the wavelengths from a rack into two sets. One for intra-rack and intra-cluster, and one for inter-cluster. And the AWGR that I showed you is used for this intra-cluster communication. Okay? So this is a high bandwidth network. Okay? It's got fixed connectivity, so it is not possible to use it to send data to every other rack within the cluster. It depends on how many wavelengths and how many transceivers you use, but it is possible to use multiple hops. That is, go to another rack and then ask that rack to switch it to the destination rack and so on. Okay? So that's what we use for the intra-cluster network. And this is for the inter-cluster network. Okay? So I can configure my clusters, and after the clusters are configured, I have those clusters connected together using a topology. And that topology is also changeable, configurable. Okay? So that's obtained by using a combination of a simple blend switch and the wavelength selective switches. So I can change both the topology and the bandwidth of the links in that topology. Okay? So now the clusters are also connected together. So if a rack wants to send something to another rack, if it's within the cluster, it's going to use that AWGR that I showed you in the previous one. If it's outside the cluster, then it's going to send it to the inter-cluster network. Right? So that's the receiving side corresponding with the transmission side. Okay. So I'm going to show you a few sampled results now. Okay. So this shows the evaluation of how many hops it takes to go from a source rack to a destination rack. And by hop, I mean the number of intermediate racks that I need to switch in. Okay, that's the one that contributes to latency. Okay. So this is with a Facebook trace from a real data center, right? So if you look at this, is OSA is the one that I talked about a little bit earlier. Factory is the conventional factory architecture. I didn't talk about this one, but this is a non-configurable optical architecture, and this is the architecture that we just presented, ours. So if you look at the number of hops, so that, our architecture has the smallest number of hops for this, real-world trace, and we also measure here the amount of traffic that is going to be switched by each top on average, because that is an important. If you're going to, if a TOR switch is going to switch traffic on behalf of, other racks, okay, then that shouldn't be too high, because that becomes the bottleneck then. Okay? So it turns out that that is also pretty low. But here are some cost and power numbers for these components that I have introduced. So these are the electronic components right at the top, and usually it's about 50 watts per port, okay, for an electronic switch. And for the network interface card, it's about 4 watts per port. And that's the cost. Again, this is per port cost, about $3,000 for a switch, and about $1,000 for a NIC, network interface card. So quite expensive devices. So if you look at a 50-port switch, you can, that's over $150,000 for a switch, right? Okay, these are some of the optical components. You see, many of these are zero because many of these are passive devices, so they don't consume any power. Okay, and the costs are also pretty reasonable. Well, this is an expensive device, as I mentioned. WSS, the wavelength selective switch. That's more than $1,000 per port. So right now, 20 is the maximum number of ports that you have, but that's upwards of $25,000, something like $25,000 right now. Okay, that's 20-port switch. Okay. And this is the number of components of different types in each of the different architectures. So if you use these numbers and look at the x-axis here is the size of the data center, the number of racks that you have, and it can go as large as to 1 million. So if you plot the power and the cost, this is how the three architecture behave. That's wave cube, this is fat tree, and this is our architecture. So much lower cost and much lower power. Okay, I'll actually skip this thing. How much time do I have? Just a few minutes? I'll just to take a few more minutes. So here is another optical architecture which is very interesting. It completely gets rid of fiber. Okay, turns out that cable complexity is a big thing. Okay, I mean you saw the figure that I showed you at the very beginning. It looked really messy, right? Well, all these cables patched from one place to another. It's easy to make a mistake and plug a cable into the wrong port, right? So this design basically completely gets rid of cables by using wireless. Now it turns out that if you're using RF, that's prone to interference and doesn't provide the bandwidth that you need for these applications. Actually, it's not the standard RF band. You have to go to millimeter, so-called millimeter wave band, or 60 gigahertz band, but that turns out to be not very focused. The energy radiates out too much. It's practically not usable. So they proposed using fiber optic, free space optics. Okay, so here is their idea. So you have these racks here, and your ceiling is full of mirrors. Okay, and you take the traffic pattern. There's a Firefly that's called Firefly. It's the name of the design. So you have a Firefly controller that tells these guys which tracks you're going to connect to and how the transmitters and mirrors are going to be tilted. Okay, so it's this free space optic communication where your transceiver is going to be steered. You have a steerable transceiver on top of the rack, and then the mirrors are also steerable at the top here. And they showed two kinds of mirror designs: a switchable mirror operation that looks like this, and something called as scalable mirror. Anyway, they showed two different existing technologies for doing these mirrors, right? And they actually implemented a small prototype of this network and showed that it works. And they did some cost studies and showed that their architecture is really good in saving cable complexity and cost. So this is fiber and copper. So all of the other architectures have some fiber and copper. And Firefly, the cost is there's no fiber or copper here. It's free space optics, so the cable complexity is 0, as you see here. And the power is also pretty low. Okay. So this is a very intriguing architecture that gets rid of cables. And this is, it's much easier to do this in a data center design than in than outside, because one of the problems with free space optical communication is interference due to weather. And now we are in a controlled environment because this is indoor. Okay? So there's no fog or anything that can impair the links. Okay, I think I'm out of time. I have a few slides on how TCP, which is a protocol on the machines, is adapted for data center applications. But I don't know if I'm going to have time to go over this. Sasha, what do you think?
That's up to the audience. If the audience would like to go further, go ahead.
Should I go ahead?
Yeah.
Okay, well, a few more minutes. Okay, so again, I don't know how many of you know about TCP. You've probably heard about IP and TCP. So TCP is a major networking protocol that's being used for 40 years now, right? With almost no change. There's been some changes, but almost no change. Used in the internet for wide area network applications. So basically, what it does is it sends packets, okay, and the rate at which it sends packets starts at a low rate, and then it ramps up because it doesn't know how much bandwidth is available. It ramps up. If there is a packet that is lost because of congestion, then it ramps down. Okay, it aggressively cuts down its sending rate, and then if there's further losses, it cuts it even more. In fact, it cuts it by half. Okay, the rate at which it sends data. Okay, so that's what happens in the internet. Now, it turns out in data centers that is not a very good strategy. So there was a group, I think this was a Microsoft group, that came up with an alternative to TCP in data center called as DC TCP, data center TCP, which works as follows. So the problem here is that you have to have high burst tolerance and you have to have low latency. I keep repeating this, that's very important. and you have to have high throughput, right? So these two are sort of conflicting with each other, but they are both needed in data centers, right? So the challenge is to achieve these three things together. And the problem in data centers is that we have these, elephant flows and mice flows interacting, sharing the switch, and sharing the buffer space within the switch. It's possible for the small flows to be completely starved of bandwidth, thereby increasing the latency for these flows. Okay, that's because of the way TCP is designed. Because the high flows are going to start sending data, and they're going to be successful, and then they're going to ramp up their rate. And the short flows, if they send some data, if there is one packet that is going to be dropped, okay, then the sending transmitter has to time out. That's the way TCP is defined. It times out after a long period of time and then resends its data. So that this leads to very long latencies, right? So the TCP was modified to better deal with this by taking this change. So in the internet, the TCP is designed to react to the existence of congestion, okay? And that manifests itself as a packet drop, okay, in the internet, right? Whereas in data center, that doesn't work. So they changed it so that TCP reacts to not just the presence or absence of congestion, but to the extent of congestion, okay? So the idea was to not simply look at packet drops, but to look at what is the extent of congestion. Well, how do we achieve that? Well, this is what they did, okay? So in each of the switches, there's a certain threshold, K here. If the size of the queue, when the packets are going through the buffers at a switch, if the size of the queue is small, then you don't mark the packet. The congestion is low. Okay? There's not much waiting. But if the size of the queue is large, there are a lot of packets waiting in the queue, then you start marking these packets by setting a flag in your packet. Okay? So when the source gets this information, it's going to set the congestion. It's going to set the what's called as the congestion window, which governs the sending rate of the transmitter. Okay, it sets it according to this equation. Okay, this is I promised no equation, so I'm not going to talk about this equation, but it's a very simple equation that changes the sending rate in a much more smooth fashion compared to the standard TCP that is used in the internet. And they showed that this, by making a very simple change, it's possible to it's possible to avoid the so-called incast problem where the short-lived flows are starved of bandwidth because of the competing high bandwidth or large flows. Okay, so that's all I wanted to say about the protocol. So final thoughts. Connectivity is very important in data centers. And architectures based on electronic packet switching don't scale very well. Okay. The switches tend to become very expensive once you go to high data rates. Right now, the interfaces for most of these servers are 1 gigabit per second, but already companies are talking about making it 10 gigabits per second or even 100 gigabits per second. This is just one server. And if there are 30 servers in a rack, you can imagine the amount of the data rate coming out of a rack. Of course, not everything is going to go out of the rack, but if it's 10 gigabits per second with 30 servers, that's 300 gigabits per second for a single rack. And imagine tens of thousands of these racks, right? So the bandwidth demands are really astronomical. Okay. So optical switching has the bandwidth, okay, has the ability to deal with these kinds of bandwidth demands, but they must be used carefully with electronics because there are limitations to optics, as I mentioned, right? Okay, so I haven't talked about this, but software-defined networking is a new paradigm where you can configure the network using software control. Okay, now that is particularly useful in data centers because configurability is the name of the game here. Okay. So now, where is this going? Well, right now we have these huge hyperscale data centers. Okay. But there's also a lot of work going on about so-called edge computing, not just cloud computing, but edge computing, where you have a lot of these small-scale processing. I don't know if I should call them data centers, but small-scale data centers. So, right now we have all of the traffic going to the wireless traffic going to base stations and then onto the data center and so on. So now with the emergence of 5G, that's changing with the smaller cells, micro cells. You have base stations that could be put up on on an electric pole here. Okay, this is beginning to happen, and there are vendors that are starting to offer 5G products starting later this year. Some of them have already debuted, demonstrating some in conventions this year. Right? So all that is coming up. So the data, a lot of data is probably not going to be sent to some cloud, all the way across the country to be processed and results sent back, because the latencies would be too high. So you might do some processing closer to the user. So you might have a lot of distributed small-scale data centers and then some very large hyperscale data centers, right? The hierarchical structure. I think that's where things are going now. So I'll stop and let me give some acknowledgments. So the architecture that I presented here, that was primarily developed by two of my students, Manan Su and Lin Tian, also with a couple of collaborators, Eitan Moriano at MIT and Yelena Diaco Nicholas at Berkeley. And the work and the research that I presented today was sponsored by the US National Science Foundation. So thank you very much, and I'll be happy to answer any questions.